So today I'll be talking about drones for the transport of laboratory specimens. And on there is Jeff, the drone engineer that I work with at Hopkins. And that's it, so I'll start. So we have 3 learning objectives. The first is to describe the impact of distance on healthcare utilization, access, and cost. Second is describe an approach for evaluating the impact of new transport methods on sample viability. And the third is list what 3 challenges remain to achieving the promise of drones in healthcare. Today I'm going to talk about why we need drones in healthcare. And then I'll spend some time talking about how we actually make that happen and what are some of the challenges that remain to the promise of drones in healthcare. To address this first question, I'll show you 2 examples. The first is a video. And then I'll talk about the impact of distance on healthcare utilization and costs. So here's the first video, which is from a town called Schukmansberg in Namibia. And it has a German name because they were colonized by the Germans. All right, so Schukmansberg is in northeast Namibia by the Zambezi River, which is where it's being circled on the globe there. And for much of the year, about 6 months of the year, they have these annual floods that prevent access. So if you want to get pathology specimens from the clinic, you have to take a bridge, go into Zambia, and then do this potholed roads for about 70 kilometers. And then you cross the river again, this time going south. In our case, the police heard about our project and they sent a boat to come get us. And so that's the police driver in the back. And those are the different members of the team. And then you go through these grasses and bushes, and I have no idea how they figure out where the roads are. And then finally you arrive at Schukmansberg. And at Schukmansberg we have a clinic. There's a clinic and a nurse that works there full time. So there are services. There's just no way of getting the samples out. And to me, this represents one class of challenges, which is geographical challenges of some kinds, either mountain or river or something like that. The second example I'll show you is from a group they called me because they're interested in setting up a drone network. In this case, this is an urban example where the 2 hospital buildings are right across the street from each other, but it takes a 30-minute drive to get from one to the other. And it's because there's a highway in between, and so they have to go around. And when there's traffic, it's worse. And there are many examples of this kind also. For example, I got contacted by another hospital group in India that has trouble with transporting organs from a donor in one hospital to a recipient in another hospital because of the traffic. And as you probably know, the time in transit affects how well the organ does, and so they want to decrease that. So these are the 2 classes of problems we see often. In addition to this issues of access, we know that distance has an adverse impact on healthcare access and cost. So on this slide, I have 5 studies looking at this very issue. All the studies are from countries in Africa, but that reflects my bias. That doesn't reflect the phenomena. This phenomena that we see has been shown in studies here in the US, in Australia, and so forth. And what you can see is that in every study, the odds ratio is in the positive direction. So in the first study, for example, is from out of Gambia, and they studied 840 people. It was a case control study, and people who lived more than 6 kilometers from the health center had twice the risk of an adverse outcome as people who live closer. The study in Uganda was about 4 times the risk, and the study in Tanzania and Ethiopia were smaller relative risks or hazard ratios, but it's always positive, and so that's what we see as your distance from a healthcare center increases, your outcomes worsen. In addition, costs is also affected by distance. So what I'm showing here is the front page of a study done by the USAID on last mile costs of public health supply chains. So the last mile is defined as that portion of the supply chain that delivers a health product from the last storage point to the consumer at the service delivery point. So for example, if we had gloves that were made here in Seattle and they were going to be used in some small town in Liberia. The last mile is from the storage depot in Monrovia, which is the capital of Liberia, to that town. So what they found out doing the study is that half of what the cost for getting those gloves would be in that small town occur between Monrovia and the town. So it doesn't happen between Seattle and Monrovia. It happens that very last mile. So if we can somehow improve the efficiency of the last mile, we can have an outsized impact, positive impact on healthcare costs and access. So these are the reasons why I think we need a drone. So I'll start by now defining what a drone is. For the purposes of our talk, a drone is it's not always small, but for the purposes of all the work I do, we're only focused on small civilian drones, a small unmanned aerial object. And you can see, I put the truck there just for comparison. So it's a lot smaller than a truck. So the drone is about half the size it's about the size of Jeff's torso, and the truck here is much bigger. And it's an unmanned system. So one has a driver on board, and the other one doesn't. And it's also an aerial system where it's flying. It's not using the roads. In addition, there are different types, sort of broad classes of drones with different characteristics. And I show this because when I give this talk, I tend to get lots of questions about, how far can the drone fly and what can it carry? And some of that depends on what you want to do with it. So on the left, we have an example of a fixed wing drone. It cannot do vertical takeoff and landing, but it has a really far range. And compared to a helicopter type drone, which can do vertical takeoff and landing, but doesn't have a great range. So one way to think about this is that a plane needs a whole airport in order to land, right? So that's why we have all this kind of wasted space. But it can take you to Asia or Africa, while a helicopter can land on the top of a building, on the roof of a building, but it can't take you cross-continental. Multi-rotor has even better specificity for landing, but has really poor range. And a hybrid, the last shown on the right, has aspects of both. So last bit here, the fuel is about half of the drone's takeoff weight. And if you want to use the drone to carry a payload, which is what we want to do, we want to use it to carry medical samples, then it's always a trade-off. So the more payload you put on, the less distance you can travel for a given takeoff weight. I believe that drones are part of the future of healthcare. So today we have ambulances, cars, motorcycles, and I believe in the future it'll be just one more piece of that. I don't believe that it will replace all the rest. It'll just be one more piece of it. But I think there's sort of three things that need to be addressed to get there. The first is the stability of biologics. The second is engineering and infrastructure. So actually having the drone be more appropriate for the medical uses we want to use. For medical reasons we want to use it. And the third is regulation and public opinion. So right now the technology is way ahead of the regulation. So I'll start with talking about the first, stability of biologics. That's what has been a lot of my focus for the last couple of years. The reason I focused on stability of biologics is something that we all understand in this room, which is if the blood sample is compromised somehow, if it's hemolyzed or something else happens, or if it sits around and the glucose gets degraded or something like that, then it's just not medically useful. So we spent over the last couple of years, we've done 4 of these studies. And I'm showing the first 3. The first study focused on transport of chemistry, hematology, and coag samples. The second one focused on the transport of microbes in blood and sputum. And the third one focused on blood products. For all these studies, we had the same approach, which is we got 2 sets of samples that were as similar as we could make them. If it was from volunteers, we got 2 sets of samples from a single draw. One set was driven to the flight field and held there, and the second set was driven to the flight field and flown in the drone. And then both sets of samples were taken back to the laboratory and measured. For all the for each paper, we had different acceptability limits. This show you the criteria for acceptable performance for our chemistry, hematology, and coag paper. So we looked at acceptable limits as defined by clinical bodies. We looked at systematic error. We looked at random error and clinical reclassification. On the next few slides, I have data. I have examples of what the data look like, but you guys literally taught me how to make these figures, so I'm going to skip through most of this. The conclusion is they were fine. There was little impact of the drone flights on the samples, either for chemistry or hematology samples. Okay. In terms of the results, only bicarb did not meet the strictest criteria, which was the one from, which country do you think had the strictest criteria? Everyone always says Germany. It was Australia. Of course. Okay. There's no systematic bias. In terms of random error, the CVs for our flown samples, we did population CVs of the flown versus the terrestrial samples, were slightly higher than our in-laboratory CVs. There was probably a lot of reasons for that. One was that our time to analysis was really prolonged because we consented the donors in the morning at 7 o'clock, and by the time we collected all the samples, drove to the flight field, did all the flights, and came back, it was about 6-7 hours later. So the samples were old. In terms of our clinical reclassification, there was 97% agreement for normal samples and 84% agreement for abnormal. And what that was is if, say, my sodium from the terrestrial sample was normal, was the sample that flew on the drone somehow changed? And basically there was a high agreement for normal samples. And the agreement wasn't so good for abnormal samples because there were so few of them, because the people who we recruited to donate blood were laboratory staff. We did the similar experiments for micro. We looked at sputum samples and blood culture tubes. For the sputum samples, we collected a pool of pathogen-free, containing only normal flora samples. And we made a pool and split it up so that both sample sets were as identical as we could get them. And then we put different concentrations of microbes in each one. So we had three logs of the microbes, and we used MRSA and strep. And similar design to the first set of experiments. We flew half the samples, and the other half did not fly. We also had a similar design for the blood culture tubes. We had 6 sets of paired aerobic and anaerobic Bactec bottle culture tubes, and we inoculated them with 10 mils of whole blood from the blood bank. And in one of the samples, we had Staph aureus, we had Staph pneumo, B. frag, and E. coli. And our idea was we weren't sure if there would be an impact, so we wanted to explore aerobic and anaerobic organisms as well as those that we thought might be more fastidious. The results were from the sputum culture specimens. There was no impact of the flights, which was great. Same thing for the blood culture specimens. There was no impact of the flights. So here on the y-axis, we have the time to positivity. So at what time did the culture turn positive? And on the x-axis, we have the names of each of the organisms. And each of those dots corresponds to 6 individual blood culture tubes. And then you can see there was a lot of consistency in when they turned positive. The first time we did this experiment, the E. coli sample that was flown in the drone turned positive a lot earlier, something like a couple hours earlier than the other one. And so I was pretty excited because I thought I had proven that transporting blood cultures by drones would make them grow faster. But it turned out it was a mistake. So I thought we should just repeat that experiment. The results are too good, and they were too good. So, oh well. All right. One more. So we did the same thing again for blood products. The idea here was to systematically examine each different class of products we deal with in the lab. We look for packed red cells. We looked at temperature in flight and a hemolysis check. For platelets, we looked at temperature in flight, platelet count, and pH, and mean platelet volume. And for fresh frozen plasma, we just looked at our ability to maintain temperature in flight and pictures of bubbles as evidence of thawing on the back. The approach was similar. Red cell and platelet units were split in a sterile fashion, and one half was driven to the flight field and held, and the second half was driven to the flight field and flown in the drone. And we brought both samples back to the lab and measured it. I will show you that video. If you'll notice, this drone is a very different drone from the first one, from the one the first.
We're actually doing some tests here at Hopkins to make sure that the blood can be safely shipped by drone so that we can maintain the critically needed temperatures and the time frames that we need to do it.
Platelets.
Temperature is -21.
We flew it around for about a maximum of 25 minutes.
At Johns Hopkins, we have hospitals that we work with directly that when we identify a specific unit that may be necessary for one of their patients, we have to go through ground transportation, taxi cabs, sometimes in an emergency, even getting state police involved to get them there quicker. So potentially drones could speed that time dramatically.
All right, so this is what the results look like. Basically, the temperatures, we were able to maintain temperature of all three components during the flight. This is what the hemolysis check looked like. There was no obvious hemolysis by visual check, and all the platelets indices pre and post flight were unchanged. Same with the frozen plasma pre and post flight. So that was all great. I was feeling pretty good at this point, because I thought, okay, I've just done 3 studies which showed nothing, but it doesn't matter because nothing is a good thing in this case. So maybe we can go forward. But what happened at that point was we started getting some attention and notoriety for doing these early experiments, and started getting calls from people who actually wanted drones to fly, for real in production, so to speak, in their countries. The first one of the examples was the first video I showed you, and they said. And so we'd have these conversations like, oh, what do you want to fly? And they would say, oh, we want to fly lab specimens. And the lab we really want to get to is about 70 kilometers away. And I was like, oh, we don't do 70 kilometers. We do 20. That's what we do. So this conversation just kept happening. And I realized that my concept of what the drone could do and what was needed were not matched at all. So we decided to do this much longer, essentially repeat our initial experiments, but do it a much longer flight. So we did a 3-hour, 260-kilometer flight. The driver for this was, we thought if a lab was 100 kilometers away, which is what people were requesting, then we needed to test, a 200-kilometer flight to capture that whole to capture that, to mimic the transport time. This was at 33 degrees, and so it was much warmer also. So I'll just show you what that video looked like, because the type of drones we used for this was also different. We're looking at the viability of blood samples after long drone flights. Today, we recruited a few volunteers, obtained blood samples from them, and took half the samples and held them stationary, and took the other half of the samples and flew them on the drone for 3 hours. Once the flights were completed, we took all the samples back to the laboratory and ran a battery of tests. Then we compared the results from both sample sets. This was in the desert in Arizona, so it was pretty hot. We did the testing at Mayo Labs in Arizona. And the thing is, it's good for him to listen to them.
This has important implications for patient care, especially as we transfer specimens from one site to another.
Go back. I have this this figure on the right. Okay, so I don't have a pointer, but this figure on the right to show what the data as an example. So that each dot represents. Most of you guys know this, but we have visitors from engineering. That's why I'm going into this. Each dot represents 2 different samples, and for each paired sample, it shows the mean versus the difference. So that dot in right shows in red with the red circle around it shows 2 samples where we got the same results for the flown and the stationary samples, and so it's a 0. If you look at the results on the left for results for potassium, we have about a 6% bias overall for all the samples, and we had an 8% difference for glucose. So those are the 2 analytes that had an impact. But it makes sense because those 2 analytes are more sensitive to sitting around and to temperature and all that, and so it makes sense. But what was interesting is we think the aberration in potassium and the glucose actually came from the samples that were sitting on the ground rather than the ones on the drone, because the ones on the ground were in a car being kept cool, and the ones on the drone were in a little refrigerated unit which we had built, which you can see there in the picture on the right. And I think that kept things actually at a better temperature control than the one in the car. All right. So based on the experiments we've completed so far, medical biological materials stable when transported on drones as long as the flight is under 2 hours and temperatures are controlled. All right. So now I'll go to the second part of the talk, which for me was was kind of a new discovery, which is engineering and infrastructure. When I fell into this work by accident, basically I got into working on drones because I had a conversation with a medical student. So don't do that. And he had this idea of using drones to transport medicines in India. And they said, oh, you should go talk to Dr. Tim because he knows international stuff. He does international work. And he came to talk to me, and I thought it was a terrible idea. I thought it was just, I thought people need water, they need bicycles, they don't need drones. But once I started looking into it, my opinion changed because because of the price point of the drones, and so from there, slowly got into it. But what I expected coming into the field was that everything would be ready to go. So it'd be like a truck, you just buy one and then you drive it. And you can buy off-the-shelf drones, but they're not a good fit for what we medical people are trying to do, and I'll explain in a bit. So I have this picture of a Tesla and the picture of a road to try to illustrate what I mean by engineering and infrastructure. It's not necessarily what everyone else means. So the Tesla, I don't know if many of you have been fortunate enough to see the hood, what the hood looks like. It looks like a trunk basically, because there's no combustion engine in there, so it's just empty space. And to me, that's engineering is something that changes the attributes of whatever tool it is that you're building. And so that's what I mean by engineering. And on the right are all the things. Infrastructure to me are all the things that you need for your machine to work. So a Tesla is great, but without the road and without science and without this whole ecosystem around it, it doesn't work. And I've found that we've had to do a lot of building of both the pieces, and I wanted to share that with you. Another example of engineering, this is what beds have always looked like for centuries. This picture is from 1911. But around the same time, in 1909, Dr. Gatch, who was a surgery resident, came up with the Gatch bed, which is now the basis of all the hospital beds, essentially all the hospital beds we have. At that time, Dr. Fowler had just figured out that patients did better if they had peritonitis. They did better if they could sit up, because if you were recumbent, then the infected fluids would go up to your lungs, and people would have they would get infection and so forth. And so he had figured this out, but everyone had trouble implementing it. So there are papers out there of the use of pillows to decrease infections, or the use of wooden boxes to decrease infections in patients. But it just wasn't comfortable, it wasn't practical, you couldn't clean people appropriately. So he came up with this idea of a movable board. And to me, that's what I mean by engineering. Actually, changing the machine or the tool so that it's more appropriate for medical use. So let me try to apply that to some of what we've been doing. On the left, there are two different airframes, and one of the ones we had considered is the one in the back in white. When you open up the fuselage, that's what the space looks like with the battery we're hoping to use. That's what it looks like. So it takes up most of the space, and so there's really not much space for specimens, which is the whole point of what we're trying to do, is move specimens. So if you look at it closely, you'll see that it has one rotor in the back and no other rotors. So it means that this is a plane that needs basically an airport or drone ports to land. And in a lot of the small clinics, like the one I showed in the first video, there are no spaces like that. So we needed something that could take off vertically and fly. For the experiment that I showed you in Arizona, we built a cooler box to keep the samples cold. You cannot buy cooler box. You can buy cooler boxes to keep things cold, but to have a cooler box that's also light enough to fly was a challenge. So we built one, and that's an example of it. And we tested it in Arizona. Also, just for your own interest, for this flight, the extension of the fuselage on the bottom where the cooler box is being placed we also designed that. So there's a lot. For me, it's been surprising that we've had to essentially do a lot of engineering. It hasn't been as off the shelf as I just anticipated it would be. And it's all about making it appropriate for medical use. In terms of the infrastructure piece, we've designed several things. We've designed a portable drone landing port. we've built a drone biohazard transport box, and the idea of this is if you're transporting something that's biohazardous and you have an unintended landing, you want to contain everything in the box, right? If possible, you want everything contained, and there were no options out there that did that, so we built one, and I'll show you some of the testing we did for that. And also, communication devices are a problem, meaning a way to communicate without the limitations of a radio antenna. All right, so my conclusion is the infrastructure to support implementation of large medical drone transport networks doesn't yet exist, but is being developed. However, current infrastructure is robust enough to support pilot projects. All right, so now for the last piece of the 3 pieces, regulation and public opinion. We know that drones are becoming more common and more accepted. So I did a Google hobbies and leisure search for drones, and this is what you see, which is the number of searches for drones are going up every year, and there's a peak every year around Christmas. So it's getting more common, and also if we look at drones, number of drones sold per year, which is a reasonable measure of the popularity, but this doesn't tell you all the drones sold per year. It's only by the 3 major companies that report. So we have here the companies with the highest volumes. So this a company called Parrot, DJI, and 3D Robotics, and those are what their numbers look like. Went from about 100,000 or so, about 150,000 now to above 1 million, and they've for just the one company, for Parrot, and the volumes can continue to increase. So this is from 3 years ago. So they're becoming more common, but the regulation is lagging behind the technology. So only 57 of the 174 or so countries in the world have any drone regulations. And most of those 57 were outright bans rather than instructions on how to fly safe and legally. In the US, we have a tiered system, which is it's mostly a ban with the option of where you can apply for exemptions. So that's what we have in the US. But more importantly for us in this room, most of the regs are not medically appropriate. So the current regulations are based on physical designations, so altitude, are you flying the drone within line of sight? What is the weight of your drone? Is it less than 55 pounds or more than 55 pounds, and so forth? So it's based on that rather than things that are medically appropriate. So I'll give you an example based on current hazard designations. So we have here 2 kinds of cargo, which you know very well. The first is blood products, which are intended for transfusion into patients, and they're classified as non-hazardous because 100% of units are tested. So in theory, based on the hazardous designation, they are okay to fly today, but they represent a relatively small volume of the overall medical samples. So to my mind, it's not that useful to potential customers, meaning if a hospital wants to fly medical samples, it's not that useful to them to only fly the blood products. Blood specimens on the bottom are intended for testing, and then they're discarded. They're classified as potentially hazardous, and all 100% of units are eventually tested, but at the time they're flying, they haven't been tested. And so based on the hazardous designation, they're not okay to fly, but they represent the majority of the volume, and so they would be useful. And so how do we deal with that? I don't know yet, but we're working on it. So this is just an example of some of the challenges. All right, so I'm going to conclude. And the conclusion is I think drones are part of the future of healthcare, and we need to figure out the stability of biologics, the engineering infrastructure, and have more appropriate regulation to get to the future we're looking for. And that's it. I'll take questions. Yeah. This was when we were doing our first experiment, and a bunch of vultures thought, because vultures have circling behavior, so if they see you circling, they think there must be food, so or prey. So we're flying the drone around and around in circles because you can't fly beyond line of sight. And so they came out and started following it. And after about 10 minutes of that, they just decided, this bird doesn't know what it's doing. So it flew off. Yeah. Yeah. All right. Yeah.
Thanks, Tim. That was a great talk.
Thank you.
I guess my question is, in low resource settings, how much did these cost, and how often do they need to be replaced? And do you envision a network organized for a country where things are? How do you prioritize? There's tons of small communities that need this, and it seems like a pilot study is one thing, but how do you really functionalize that?
Right. So, well, I think the way to get where we want to get is just to start small and see where it goes. So the cost question is a good question, but it's almost impossible to answer. So because we use the word drone for all kinds of things. We use the word for drone for everything from what Jeff flew in the beginning of at the introduction to military aircraft. So in the sweet spot where I'm sort of targeting and working, I would say they're in the range of $10,000 to $20,000, and for that price, I think if it's set up right, meaning we don't just have drones devoted to, say, one leg of we have the drone acting as a network, so it's serving various clinics and so forth. I think it makes financial sense. I think it makes financial sense for a lot of places, including those in poor countries. For example, the video I showed in the beginning, they have a clinic that's already built. The clinic already has infrastructure, so power, water. They have a borehole. They have a nurse who's living there, who's being paid, who's working full time. So it's not like there's no investment. But right now, there's all that investment, but they're getting nothing out of it because they can't get the samples out. So this would, yeah. So I think in that setting, it would be a reasonable addition. Yeah.
3 comments. First is, people have been doing this for a long time. In 1938,
Yes.
Elmer de Gouwen published, the ability to put blood bottles in ice in milk cans and ship them from Iowa City all the way to Denver and back,
Yeah.
and then in airplanes and fly them all the way to San Francisco
Yeah.
and back. And in the military, we certainly worry about the ability to move large amounts of blood. I've dropped 3,600 units of plasma out of the back of a C-130 using a parachute extraction device, bounced them down the runway, and discovered that 48% of the plasma bags will fracture in the cold just because they're brittle. Mm-hmm. Mm-hmm. Finally, just now that we have...
I want the reference to that study, the plasma study. I do. I want...
that one actually doesn't exist. The de Gouwen one is published in 1938. Okay. The final thing is that we're putting blood on our helicopters now, and have discovered that as traffic gets worse in King County, increasingly the ambulances are calling on the helicopter to remove the patient from the ambulance and take them by helicopter to the hospital. And the number of calls for that have gone up from about 3 a month in the summer to about 40 a month, just because we can get the patients out and move quickly.
Great talk, Tim. It's great to have you back here. So
Thank you.
This is my former chief resident, too. So my question is, as a drone naive person, what is the role of a human driver? What's the human interaction with these drones right now and in the future as you see it?
Yeah. So the big disclaimer is, I don't know what I'm doing, but I probably know more than everyone else. So I think no one knows what we're doing yet. So our vision is that we'll have a person with some training / expertise at a hub. And then we'll have maybe, say, 5 clinics or 10 clinics that are serviced by this. And there'll be different tiers of training. So the person at the hub will know how to monitor flights, how to maybe take over in case of emergencies, how to set up the schedule, so things like that. How to inspect the drones for scheduled inspections, things like that. And then at the clinics, we'll have a second tier of workers. So it's say nurses or clinical lab scientists that are trained to interact with the drone safely. So they're not doing the inspection, they're not doing, but they know how to make sure the rotor has stopped spinning. They know how to, if there's a need to swap out the batteries, they've been trained in doing that. So that's kind of the vision in my head, but who knows how it'll actually work out.
Even more naive, just there. Nobody needs to actually be holding a joystick or something like we saw in the field there. I mean, this will be just programmed all the way through. Okay, I assumed that was the case.
Yeah, correct.
Tim?
Yeah.
Yeah, thanks. Great talk. Because I'm sure you've gotten asked this a bunch, we'd like to hear the few-minute version of the answer for this. If you have to do all this development work, there's a lot of research to be done, there's a lot of investment to be done. Why not figure out how to put point-of-care testing or laboratory infrastructure in all these places? That's also a very difficult problem that we know is very difficult to solve. Why is this a more solvable problem than putting laboratory? Why central labs and drones versus lots and lots and lots more labs?
Oh, versus point-of-care labs everywhere?
Yeah.
In every village?
Yeah. Drawing on your perspective and your experience with point-of-care labs everywhere.
Well, point-of-care labs are still labs. You still need to do controls. I mean, you still need all the things you require to make a lab run. So in a way, it's easier to have a transport system and have one good lab that's controlled than have. Yeah, it's. I mean, so this discussion has been happening for decades. You know this, and point-of-care testing is more expensive and less accurate. I just don't think. It would, yeah. It's same reason we don't do it here. It's a terrible logistical approach to set up to have the core of your testing based on only point of care testing. I think it makes sense to have key tests that have to be done at the point of care. But it's really hard to maintain the quality of testing if you're doing all point of care. Drones are sometimes I wonder if they're an overpowered solution to pretty straightforward problems. But I challenge anyone to suggest a better solution to an example like the one I showed in the beginning of the talk. And there are many of those examples. That one just happened to be in Namibia. We've seen examples like that in Canada. So it's just, I think part of the reason why there's so much excitement around trying to use drones is that there are problems like that cannot be, to my mind, cannot be fixed any other way. Yeah.
Hi, Tim.
Chris?
Oh,
Yeah.
hi.
Oh, Chris. Yeah, you should. We have an actual aerospace guy in the audience, so you guys ask him all your engineering questions.
I don't have an engineering question.
Oh, okay.
But that was a great talk. I think
you.
that chemistry stabilities and stability of analytes is really important, but we kind of let a lot of that go under the table. Like things sit in courier boxes for 12 hours. We don't really even know what the courier, how he's driving, if he stopped at McDonald's, like what happened. But one of the things that I would think about is how will you get the results back to the lab and things like that, and labeling.
Yes.
Of course. Particularly in the not in Canada where you can just
So I'll give you a specific answer to that question, but not a general answer. So it will depend on it. But in where we're hoping to work in Northeast Namibia, they already have a system for reporting results. It's an SMS system. And so that's taken care of, which is great. So now, the piece that they're missing is getting the samples there on time. It's actually a pretty cool system. They have printers in all the clinics, and once it's resulted in the central lab, it just prints out. So it's great. It's a great system, yeah. And I think these are all, since we're process people, we have to think about the whole process, and I think that makes sense. Yeah, Chris.
Yeah, I just had a question.
So that's the real aerospace guy in the room, guys. Everyone.
Well, I'm really glad that you pointed out that it seems to be like the regulation is one of the major hurdles here in the United States. You know, we have the most complicated airspace system. We have the most regulation. You know, Amazon Prime, you know, they're testing north of the border in Canada. They're delivering already to people in England. Canada and China have very much more open regulatory frameworks. And I guess if your customers are also the ones abroad, like in Namibia, and I guess, isn't this going to happen somewhere other than the U.S. first? Is there a reason that we want to be trying to push this technology development here in the United States, or why not go international for a proof of concept?
Yeah, that's what I'm doing. I'm literally going international for a proof of concept.
So do you think this will happen somewhere else first before it is a product in the United States?
Yeah. In fact, it's already happening. So Zipline, which is a drone company, has, I think, for the last maybe year and a half, I'm not sure, has been delivering blood products. So just the blood products which go into people's veins. They've been delivering that in Rwanda using drones for the last year and a half. The data is not public, so we don't know how many units. We don't know if the units got broken, you know, and so we don't know any of that. But they've been working there, and they have fleets and staff, and so it's already happening outside the U.S. faster because, our environment is much more restrictive.
Hey, Tim, that was great. So it must be really hard at this point to project how much it will cost, right? I mean, these are all prototypes. But is it possible to ask what is the additional cost per specimen that you can actually tolerate, and then kind of work backwards to what is the cost you need to shoot for one of these systems and the associated infrastructure? And do you see that as being feasible in the short term?
Yeah, so this is an issue I deal with all the time, including on Monday. We had a whole call about it. I think that the most honest answer is we don't know. We know how much. We know that it's like the first rocket, right? It costs $1 billion, and then the 10th one costs $50 million or something like that. You know, so we know how much it would cost to buy a drone. We don't actually know how much it would cost to completely implement. This is part of the data I hope to collect. Like, you know, it's because you got to train people, and you need to buy all these extra batteries to stay in the clinics. And if they don't have a mechanism for charging them, then you have to buy that. And you know, just thinking, so I don't know. Yeah, I don't know. But they're good questions, and they're questions that I am thinking about and hope to collect data on. Yeah.
So I have a question about commercialization. And what is your approach to intellectual property? Do you just make everything open source, or do you try to patent? And how do you hope to have companies adopt it?
Well, right now I'm not selling anything, so it's not an issue. In the future, I'm hoping it'll be an issue, that I have something of value, and we'll see. I don't really know how I'll deal with intellectual property. Part of the reason is, again, I fell into this work. My core interest, and it remains my core interest, is understanding the laboratory market in poor countries, especially. So I've mostly focused in sub-Saharan Africa. I've done a bunch of studies on that, and that's always been my focus. The drone work happened sort of accidentally, and I fell into it, and now I really see the value in it, because I get feedback that, for example, that most people don't get, because you don't get the calls that I get saying, we really need a drone network, and it's like every week, because I have this and that problem. So I have a lot of confidence that this will be valuable once the kinks are worked out, and so sorry, it's a long answer. The short answer is I hadn't thought about intellectual property because I didn't think I was creating any. Now I'm sort of, I showed you examples of where we're actually building things and doing engineering. So I will have to think about it.